Hello everyone, welcome back to our video recap. This week we're going to talking about Lab 7. We will implement the store word, load word, and the memory. Actually, for the Lab 7, there's a lot of work to do, so you should start early and be patient to go through our video recap and to do all the requirements. So last week for Lab 6, actually we create a basic structure to support R-type and I-type instruction. And for this week, we will extend it to support more instructions to store word, load word, of course, and we have to add the data memory. So if you open the Lab 7 instruction document, you can see on this page, here the figure 2 will show you the whole structure for the Lab 7. Apparently all the blue parts is the new parts we will add for this lab. The black one actually is the Lab 6. So right now we still have the register, the ALU, the mux, and the control science 10 parts. And we add one more mux for the register destination, and here is the data memory. And after that, there's another mux to the register source. So the key points for this structure is we add more output port from control unit, and we add one more data memory module. Okay, after you open the ISE project, here are the signals you need to use for this lab. You can see here there's a lot of signal name begin with the control underscore. As I said last lab, there's our protocol. All the output signals comes from the control unit. It starts with control underscore. So you know this all the signals to control the mux to support different instruction. So first is still the instruction fetch. It goes break down the 4 parts. It goes to the opcode RD, RS, and RT. And for this time, the control unit is need more output, and the register is set up as 0, but based on pay attention to different. So first, the AD data, the write back data is comes from the mux, and the load this time is not 1 anymore. The load is another signal called register load. It still comes from the control unit. And the C address for this time is the register destination max output. The RS and RT is as 0 the same. The sign extent is RT, the sign extent out, the same thing with the Lab 6. And the 2-1 mux, here is the first part, the control the register destination. The input port is RT and RD, and the section signal is from the control unit. So as I said before, this mux actually is just for the load word or the store word. The execution part, so the mux is from the Lab 6. So you know the first part is RT data, and the second part is from the sign extent. This is the R type, and this is the I type, and this is the output. And this output goes to the ALU, and everything the same. Okay, here's for your part, I gave you the cout, or you can, if you don't understand about the cout, the carry part, you can leave it open like this. So either way, you can give the cout signal or leave it open. Okay, for this week, we extend the memory parts and the write back part. So the memory is the new module we have for the memory. And you have several ports. The important one is the read enable, write enable address, and data in and data out. So that's the important ports. The read enable and write enable comes from the control unit. It's controlled. The address is the results comes from the ALU. because if you want to use the load word or store word, you have to calculate the address and give the address give it address to the memory. Data in is the RT data. So if you want to write something into the memory, which is store word, you have to read from the RT and put the RT values into the data. And the data out is if you want to load word, you give the address, give the read enable, and the output is the value in the memory. Okay, so memory dump right now is for debugging purpose, and we can give it 0. So last part is the write back. The write back is 3-1 max, so be careful, the selection signal right now is 2 bits. The first input port is the memory output. The second one is from the ALU readouts. So if the instruction is not store word or load word, you can just give the ALU readouts goes back to the register, which is the typical RTAP instruction. And the third port right now we give it 0 because this is for future extension purpose. So the output is register destination of max output, and actually this port goes back to the register. Register 88 is here. Okay, that is the top module, and the important part is I will show you is the control unit. So right now, this time the control unit have a lot of output. So based on different instruction, you have to control the different give the different values for these control signals. So I strongly suggest you to come to our lab session and we'll go through this part on the whiteboard during the class. So for the addition, the subtraction, or this typical RTAP instruction, and then we have the ITAP add R and the sub I. So that is the basic structure we have. So I can stop here a little bit. You can pause and to see the details for the old signals. And here is the OR to an I type instruction. Logic OR at I and the sub I. So this week we have supports the load word and the store word. So if the load word for both case, the ALU will do the addition to calculate the results, the address. So this 00 to the opcode. Source code it's 1 is because the load word store word is still ITAP instruction, and here destination is 0, load is 1. But you see, for the store word, the load is 0 because we don't want to write back or write anything into the register. The register source is 01 for the store word, 00 for load word. And for read, load word is memory read, and the store word is memory write. So this is quite straightforward. And we have the set less than for the next lab. So that is the control unit. So after you finish these two parts, so we can simulate it. Here is the results. Let me show you the results. So for this case, for this lab, we need one more signal besides the instruction and the register file. Okay, if you forgot how to put the register here, so let me show you. On the left side, click the UUT and click the register. The last signal, the register, is this register signal. So drag this to the wave. And one more is from the data memory. So we click the memory 0 and find the MEM signal. Okay, there is indicate this how many bits are there. Okay, so I drag this to add to the wave window, and the same thing, we change all of them, the radix to the sign decimal number. Okay, so let's open that and to simulate it. And click here, zoom to full view to show the results. Okay, here are the results. Oh, my bad, so I forgot this one. my bad, I clicked the wrong one, which needed sign decimal. Okay, here we go. For this case, we have the number 5, and for this instruction, the second instruction, this one. So this is the memory, the value is in the memory. So we have a number 5 here. So for this instruction, the C300, so we actually so make sure that the test bench for the C300, so we save the values from the R0, offset is 0 to the R3. This is the address. We stored the value in the R3 to this address. So the address is 0, so we put 5 to the memory. So store word is okay. So the same thing, so you can check the results for register and the memory. You can test your load word and the store word. And give me the screenshot for the wave, and also fill in the blanks for this table. And the table, I have another screenshot for that. This is the requirements for the Lab 7. Okay, so this is quite long, so be patient to finish all of them. Thank you so much. See you next time.